Now that we have a little bit of understanding about how isomorphisms and isomorphic rings work, we're going to get a little bit more formal and get to the formal definition of an isomorphism. So first we're going to ask, what does it mean for two elements to be in the same place of their addition and multiplication tables? If you remember how the addition and multiplication tables looked, in particular if they looked the same or not, was very important in us determining whether two rings are isomorphic. So that's going to be important for us to nail down. And then we're going to use this answer to this question to develop the formal definition of an isomorphism, along with a couple of other concepts that you studied back in your Math 210 days. And then we're going to apply that definition to an example. We're going to show a pair of rings that are isomorphic and prove it. So let's think about two rings R and S, and suppose that phi from R to S is an isomorphism. In other words, it tells us when elements in R play the same role in S, and it tells us why R and S have the same structure, that they're isomorphic. What does this mean? Well, this means that basically R and S are the same ring. Now that's kind of vague. Let's see if we can nail this down a little bit. But what it means in terms of our language is that R and S are isomorphic, or there's some kind of isomorphism between R and S. And that little equal sign with a little squiggly on top, that's just a symbol that means isomorphic. So R is isomorphic to S. And what it tells us is that phi, this function, matches up elements of R and S that are in the same place in their addition and multiplication tables when we match them up appropriately. So we're going to use our understanding about how these isomorphisms work to make a more precise definition, to make it much less vague. All right, so suppose we have two elements A and B in our ring R. And let's see what the additional tables look like in R and in S. Remember, we're assuming we have an isomorphism that goes from R to S. A and B are in R, phi of A and phi of B are going to be in S. So in R, here is exactly what the multiplication table looks like. Exactly is maybe a strong word, but what we have is A is going to show up somewhere on the left, and so is B, and then A and B are also going to show up somewhere on the top, so that we can figure out how addition is going to work. And then something similar is going to happen with phi of A and phi of B. And notice that I put phi of A in the exact same spot in the addition table for S as A was for R, and I put phi of B in the same spots in the additional table for S as I did for B in R. And the reason is because that the way isomorphism works, they should be in the same place in the addition table in terms of what role they play in the rings. All right, so let's see. So we know how addition works, right? The element that's across from A and below B, that's going to be A plus B. That's the definition of how our additional table works. And now let's see what happens if we do the same thing with phi of A and phi of B. Well, I put a question mark in there because there are actually two answers to the question, what belongs where that question mark is, across from phi of A and across and down from phi of B. Well, the first thing is, we know it's across from phi of A, we know it's below phi of B, and by the definition of an addition table, that should be phi of A plus phi of B, right? That's just how addition works. On the other hand, it's also in the same spot in the addition table for S as A plus B is in the additional table for R. And since they corresponding elements in those two addition tables should correspond by phi, that tells us that it also has to be phi of A plus B. So that spot has to be phi of A plus phi of B. It also has to be phi of A plus B. That means those things must be equal. So we got to have phi of A plus B equal phi of A plus phi of B. If we play the same game with multiplication, it's going to work out exactly the same way, right? So we're going to have A and B somewhere in the multiplication table. We're going to have phi of A and phi of B in the exact same spots of the multiplication table for S. If we look at A times B, which is right across from A and right below B, and then look at the spot right across from phi of A and right below phi of B, once again, what we put in that question mark has two good answers. On the one hand, the way multiplication tables work, it should be phi of A times phi of B. But also, it's in the same spot in the multiplication table for S as AB is for R, which means it has to be phi of AB. And so it has to be both of those things. They have to be equal. So phi of AB equals phi of A times phi of B. And that basically tells us what it means to be an isomorphism. except that there are actually two more properties that we'll see in a little bit when we get to the formal definition. All right, so I think we're ready for a formal definition of what an isomorphism is. So let R and S be rings. An isomorphism is a function phi from R to S such that four things happen. First of all, and this is one that's new to us for this video anyway, it has to be the fact that phi is 1-to-1, or depending on the language that you use in Math 210, phi has to be injective. And the reason for this is that if phi is not 1-to-1, then you have two elements in R that have to be in the same spot in the multiplication table for S. And since each spot in the multiplication table for S, there's only room for one, you can't have two elements going in the same spot. In a similar way, phi has to be onto. And again, depending on the language you use back in your Math 210 days, that means that phi is surjective. And the reason that has to be is you can't have any elements in S that don't have a single spot for an element in R. Every element in S has to correspond to some element of R, because otherwise it's going to be a different ring. Now the last two properties are the ones we were just working on. If we have two elements A, B, and R, we have to have phi of A plus B equals phi of A plus phi of B. If we have A and B and R, we also have to have phi of A times B equals phi of A times phi of B. All right, so let's look at an example of two rings and show that they're an isomorphism. Our first ring R is going to be the direct sum of the real numbers with the real numbers. So we're talking about ordered pairs where the x and y coordinates are both real numbers. And then we're going to talk about a subring of the 2x2 matrices that is going to be the set of all 2x2 matrices where the upper right entries and the lower left entries are 0, and the other entries can be any real numbers. So the theorem is that R is isomorphic to S, and we're going to go ahead and prove that. So of course, if we want to prove that they're isomorphism, we've actually got to come up with an isomorphism between those two rings. So we need a function phi with domain R and codomain S, and then the way we're going to define it is in what I think is a pretty natural way, or at least a good guess of what you think that it should be. If you take an ordered pair in R, A, B, where A and B are both real numbers, we are going to have the output being A in the upper left, B in the lower right, and the other two entries being 0. And we're going to prove that that's an isomorphism. So we got to prove four things, right? First of all, we got to prove that phi is 1-to-1 or injective, depending on the language that you're used to. So to do that, the way that those proofs started was we assume that phi of AB is equal to phi of CD, and then we're going to show that AB and CD are the same. So we know that phi of AB is equal to phi of CD. That's just our assumption. Now we're just going to use what phi of AB means. There's phi of AB has A in the upper left, B in the lower right, zeros everywhere else. Phi of CD has C in the upper left, D in the lower right, and zeros everywhere else. Now, the way that equality of matrices works is each of the corresponding entries have to be equal. That means A has to be C and B has to be D. The other two entries are just fine. They're just 0 equals 0. So they don't give us any new information, but they also don't offer us anything that's contradictory. But if A is equal to C and B is equal to D, that means the ordered pairs A, B, and C, D are the same, right? Their x coordinates are the same, their y coordinates are the same. That means the ordered pairs are the same, which is exactly what we wanted to prove. All right, so now we want to prove that phi is onto. So we want to take an arbitrary element in the codomain. I'm going to call it y. We're going to give it a real name later. But y is in the codomain, and we want to show that there's some x in the domain such that phi of x equals y. Now, of course, y is in the codomain, which means that y has to be a matrix. That means y is equal to, well, some matrix where you have some real number A in the upper left, some real number B in the lower right, and the other two entries are 0. And notice that whatever those A and B are, that if I put A in the x coordinate and B in the y coordinate in an ordered pair, that's going to be in R. That's going to be an ordered pair with real numbers in the x and y coordinate. Which means that if I want to, I can take that A, B and put it into my phi. And let's see what happens when I do. Well, the definition of phi of AB is I put the A in the upper left, the B in the lower right, and zeros everywhere else. And that happens to be what Y is. And so that means that phi is onto, phi is surjective. All right, two more things that we have to check. We have to check that phi preserves addition. That's what we call that third condition that we have to show. In other words, we're going to assume that A, B, and CD are in R. And we're going to show that phi of AB plus CD is equal to phi of AB plus phi of CD. So we're going to compute each of those independently and make sure we get the same thing for both. So if we look at phi of AB plus CD, the way we define addition in direct sums is we add the x coordinates, we add the y coordinates. So we get phi of A plus C rather, comma B plus D. And then the way phi works is we take our x coordinate and we put it in the upper left, we take our y coordinate and we put it in the lower right, and then we put zeros everywhere else, like that. And that's what we get for phi of AB plus CD. Let's go ahead and do the same thing for phi of AB plus phi of CD. Phi of AB, we put A in the upper left, B in the lower right, and zeros everywhere else. Phi of CD, we put C in the upper left, D in the lower right, and zeros everywhere else. And then the way addition of matrices works, we just add the corresponding entries. So we get A plus C in the upper left, B plus D in the lower right. I'm pretty sure 0 plus 0 equals 0, so the upper right and lower left are going to be 0. And notice that we got the exact same thing there as we got for phi of AB plus CD, which means that those two things are equal, which is exactly what we wanted to prove. For multiplication, it's going to be exactly the same, or almost exactly the same, just a different operation. So we're going to assume that A, B, and CD are in R. We're going to show that phi of AB times CD is equal to phi of AB times phi of CD. So again, the definition of multiplication for the direct sum is going to be we multiply the x coordinates, we multiply the y coordinates, and then we stick the x coordinate, that AC, up in the upper left, and that y coordinate BD in the lower right, and put zeros everywhere else. Now, when we multiply these two matrices, the phi of AB and phi of CD, notice that when let's say we do the first row and first column, we're going to get A times C plus 0 times 0. That's going to be AC. If we do the second row, second column, we're going to get 0 times 0 plus B times D. And if you check the other two, you'll see that you get 0. And so again, you get AC in the upper left, BD in the lower right, and zeros everywhere else. And that means phi of AB times CD is equal to phi of AB times phi of CD. And that finishes the proof that they're isomorphic. That means that phi is an isomorphism, and therefore R and S are isomorphic. So now I think you're ready to work on the activities for ring isomorphisms. That's on the PDF included with this video. And there are actually two in-class activities, and you're ready to work on both of them.